Hello, hello. Can you guys just, before we get started, please confirm that you guys can hear me so that we can get started. Perfect, perfect, perfect. Okay, cool. So last time we stopped, which is last week, we did just some basic examples of how to tackle questions, how to utilize the formulas, right? This week, what we are going to do is we are going to good morning, sir. Does physics also have extra classes or it's just maths? We're going to I think we're going to introduce an extra physics class. We're gonna should confirm it by today, and then we'll contact you guys. Okay, so yeah, so we just understood how to utilize the formulas. Okay, today we're going to continue, and we're going to continue with graphs, and I'm trying to understand these graphs. So the first graph we're going to go through is the velocity versus time graph. Okay. It will be messaged in the group for the price. So just be on the lookout for that. Okay. So the first one we're going to go through is the velocity versus time graph. Okay. Now, let's ignore that. Now, the velocity versus time graph, okay, don't complicate it. It has two possible shapes, right? And ironically, they look like a V. So it has one possible shape to look like this, okay, and the other possible shape to look like that. That's it. So, for example, if you have a velocity versus time graph, whatever it does, wherever it goes, whatever it's doing, it cannot, in one single graph, okay, in one single graph, it cannot have a different shape to either that or that one. It cannot. You'll never find a velocity time graph like this. Never. You'll never find a velocity time graph that has this, and then that. Never. Okay. And one velocity versus time graph will always have a constant shape. Okay. Which one? Because there's two options, right? When do we have which shape? Okay. So the first one on the left is when we take up as positive, our velocity versus time graph, all of the parts, all of the compartments of it are going to look like that. Okay. And this is for vertical projectile motion section, that is. Right. Of course, in different sections, you can find velocity time graphs that look different, but this is strictly for velocity, vertical projectile motion. There's only two options. Okay. So when we take up as positive, right, we need to remember that the gradient, firstly, we need to note that in the velocity versus time graph, gradient is acceleration. The gradient is acceleration. The gradient is basically 9,8 in magnitude. So remember, when we take up as positive, isn't down is negative, right? So when you take up is positive, down is negative, right? That makes sense. So therefore, acceleration is negative, definitely. So when you take up is positive, you have a negative acceleration mainly. That's the important thing. When you take up as positive, you have a negative acceleration. Remember, acceleration is gradient, so therefore we have a negative gradient. As you can see, it's a decreasing graph. Maybe it's a bit too steep, I don't know. But it's a decreasing slope, so this is a negative gradient. And actually, the gradient is negative 9,8. Okay, and if it's acceleration, meters per second to the negative 2. Hope that makes sense. Okay, so one more time. When we take up as positive, we have a negative acceleration, of course, because acceleration is always downwards, right? In that case, since gradient is acceleration, we have a negative gradient. And that's how we can remember that when we take up as positive, this is the graph we should be following. However, when we take down as positive, now let's think of this. When we take down as positive, we have a positive acceleration. When we have a positive acceleration, that means gradient is positive. That means we have a positive slope, positive 9,8 meters per second to the minus 2. That's why we can see that this is actually an increasing graph with an increasing gradient, or like a positive gradient. Okay, so I hope that makes sense. Please, again, don't complicate the velocity versus time graph. There are only two options. If you are drawing a velocity time graph and you find yourself drawing a different shape, there's something wrong. So if you start off like this, the rest of your graph, no matter where it is, maybe sometimes it continues down here, but it's going to have to be that same shape. All parts of your velocity versus time graph have to be parallel to one another. Okay, if we have it where up is taken as positive, then it's going to look something like this. All of them have to be parallel to one another. They all should have the same gradient. Remember, because gradient in this section is constant. What is gradient? Acceleration. Acceleration in this section is constant. Right? Acceleration is 9,8 downwards. 9,8 meters per second to the negative 2. Okay, let's have a look at acceleration versus time. So we just look at the first one. Now, acceleration versus time is constant, right? So it's never going to change. So in this case, can somebody tell me in this graph, right? Since I have my acceleration versus time, and below the x-axis, I have an acceleration of negative 9,8. What does that indicate to me? Which direction, according to this graph, which direction was taken as positive? Since I have a negative acceleration, which direction was taken as positive? Most definitely up. So that's another thing we need to note, is that from the graph, maybe sometimes in some questions, right, you are able to choose which direction you want to take as positive. However, when you are given a graph, that graph is going to choose the direction that you need to take as positive. Okay, let's think of it. If we have a velocity time graph and it looks like this, you're like, oh, okay, I have a positive slope. I have a positive gradient. That means that acceleration is positive. And if I have positive acceleration, that means, oh, down was taken as positive. Okay, in this, if you get a graph like that, right, you have to decipher that. Then if you're getting a graph like this, and you're like, oh, okay, I see I have a negative gradient. It's the slope is negative, it's decreasing. So acceleration is negative. Since acceleration is negative, that means up was taken as positive. Okay, so when the graph is given to you, that in that case, yes, you have to, they give you the direction as positive or negative. So this here is the same thing. Okay, in this case, of course, down was taken as positive because we have a positive acceleration, 9,8. So what is this break between 0,6 and 0,7 seconds? It is basically contact time. I just put an example. It's not that common that they ask you to show contact time. It's not that common that they ask you to firstly draw an acceleration versus time graph, number one. Number two, it's not even less common that they ask you to show the contact time in an acceleration versus time graph. Maybe in other graphs, they will, right? But in an acceleration versus time graph, yeah. But nevertheless, this is how you would show it, okay? So during contact time, there's obviously no acceleration. So in this time here, okay, there was the object was in contact with whatever it was in contact with, maybe the ground if it's a bouncing ball, and there was no acceleration. Therefore, the acceleration graph disappeared for that split second and then came back to being 9.8. Okay, so that's velocity versus time graph, acceleration versus time graph explained. We will be going through an example, right? Let's look at a position versus time graph. So position versus time graphs, they may be a bit easier to read because they sort of depict the movement in a way, right? It's sort of the projectile of the ball kind of looks like how the graph looks. Okay, it's kind of shaped like the graph, right? So let's look at the first instance, right? We're not gonna sit here and go through like every possible scenario, but as long as we understand the gist of it, okay, then it's fine. All right. So the first position versus time graph. Okay, cool. The first position versus time graph. First thing we need to note is the reference point. The reference point is your 0x axis. Now, in most cases, your reference point is the ground. So 0 meters is referred to as the ground. Okay, so now that makes sense because the ground is like, has no height. Okay, so when the ground is made reference, that makes a lot of sense, right? So in this case, we can see that on the onset, right, when time is equal to 0 at that point there, the ball is 30 meters above the ground. 30 meters from reference point, which is the ground in this case. And then it moves further away from the ground. So, okay, it moves further away from the ground, and then starts going closer and closer towards the ground. Now, again, remember in projectile motion, we said that it goes up, straight up, and then it goes straight down. Okay, that's why it's called vertical, okay, because there's no horizontal motion whatsoever. So in this case, why does it stretch horizontally? Why does it not just show us that? Okay, this is because it's showing it as time passes by. So remember, this is a position versus time graph. So as time is passing by, at 1 second, it's 30. At 2 seconds, it's there. At 3, it's there. At 4, it's there. At 5, it's there. At 6, it's there. At 7, it's there. 8, 9, 10, 11. I don't know how many seconds this is, but basically that's the motion of the ball as we go. Okay, as we are moving with time. So that's why it's stretching out horizontally. But basically, like we consider that distance from the ground, then we can consider that distance from the ground. Okay, these are the positions relative to the ground that we actually measure each time. Okay, again, the reason it's horizontal, we have horizontal is because of time. Okay, cool. So that's that. Now, okay, so we can see that firstly, this ball, it starts its motion 30 meters above the ground, and it moves up for a second, and then it falls back down. It falls back down, it passes the point where it was initially at, and then it travels down again. Okay, so what we can say is we can describe this specific scenario. Okay, let's do this. Okay, we can actually do this if we want, however. That these are both 30 meters above the ground. Okay, so how we can describe this scenario is that the ball was thrown. And if you've done questions, you'll see that this is a common occurrence. Thrown from a platform. So this specific graph is for a ball that is thrown from a platform. Let's look at this. Okay, so this is also 30 meters. I don't know, it's not written. Okay, so that's also 30 meters above the ground. But now we notice that the ball is just going straight from 30. It's going towards the ground. It's traveling towards the ground until eventually it hits the ground. Okay, by the way, this also reaches the ground at the bottom. So in this case, okay, we can see that it doesn't increase its height above the platform because it's thrown 30 meters from the ground. So in this case, we can simply state that the ball was dropped from a platform. Okay, let's look at this slightly more complex example. So initially, we can see that the ball is at 0. So the ball starts at the ground in this case. The ball starts at the ground. So the ball starts at the ground. It goes to a height of, again, it doesn't really matter, 30. Let's just say this is 15. No, let's just say it's 20. So the ball starts at 0. Okay, you can see that it's thrown upwards. Okay, it reaches a max height of 30 meters, and then it falls back down and goes to the ground. Okay, so that's what I'm saying. This one is easier to visualize because it's almost like it's the ball's trajectory if there was horizontal motion. Okay, so yeah, it's thrown up from the ground. Okay, so that's the first part of this. It's thrown up from the ground. The ball is thrown up from ground. Now it reaches max height and then falls all the way back to the ground. Now, what can we expect when it falls to the ground? Okay, when a ball falls back to the ground, we can expect it to bounce. And that's exactly what happens, okay, with contact time. Okay, so in between we have a split second, whatever it is, right? It's not specific in these examples, but a split second, half a second, whatever it is, that there's no motion of the ball. The ball, there's no graph for that region. Okay, that's just because the ball is in contact with the ground and it's not changing its position from 0. It's stuck on 0, 0, 0 for a split second. And thereafter it bounces again. So we can see that it's basically, okay, in this case, it's not thrown up from the ground, but it uses that momentum and that force of it being thrown the first time. It bounces and it reaches max height again and then falls to the ground again. So it could bounce a third time as well. But basically, ball is thrown up from the ground with a bounce. Okay, so that's important to know. These are 3 different position versus time graphs that we need to understand. Okay, now, all of these examples, as you can see as depicted here, all of these examples are for when up is taken as positive. So graphs 1, 2, and 3 are for when up is taken as positive. All of them would flip on the x-axis if down is taken as positive. So in this specific case, right, let's have a look at this. When down is taken as positive, okay, remember, the upward direction is now negative because down is taken as positive. So in this case, it actually starts negative 30 meters away from the ground. That's why it has to be below. Why negative 30? Because if we consider the ground and we consider our platform, the platform relative to the ground is above it. The platform is above it. So since the platform relative to the ground is above it, it's actually in the positive direction. Sorry, it's actually in the upward direction. So the platform is in the upward direction to the ground. Now, in this specific scenario, down is positive and therefore up is negative. Since up is negative, that's why we would indicate that its starting position is that actually it's at negative 30. The motion would be exact the same. It would be flipped upon the x-axis and it would reach there in a certain amount of time. It would reach a max height and then fall back to the ground. Okay, so that's important to note, and it would be the same for the rest of them. Okay, so even if it's confusing, what you could do is draw your positive graph and then flip it upon the x-axis. Let's quickly talk about a graph where the reference point is not the ground. Now, depending what the reference point is taken as, so let's just say the ground is actually here. Okay, no. Normally they don't do that. Let us do an example where the reference point is the platform. So remember, reference point we're going to put here. This is our reference. So if the reference point is actually the platform, okay, so I'm going to call this, I'm going to draw in a platform. In that case, remember, technically, this is 30 meters. It's going to be 0, but it is 30 meters of height above the ground. So now, with respect to the platform, we have to ask ourselves, where is the ground? The ground would be 30 meters below. So let's just say here, this would then be 0 meters. So we can refer to this as the ground. Okay, I'm just putting in a dotted line. Then we can draw our projectile. So it starts at the platform, goes higher than the platform, and returns to the ground. So in that case, that's how we draw this graph where the platform is taken as reference point. Okay, so the reference point is basically what's on our x-axis. Okay, so yes, in that case, the ground, let's write it, let's label it. This is our ground, which is 30 meters below. It's actually, technically, this would be 0. according to the units. So maybe let's just do this and this. And then, like I said, technically this would be 0. And then this would be at -30. Okay, if we're talking about just the graph stuff. Okay, but this is obviously 30 meters above the ground. So that's what I'm mentioning in red. Okay, let's move on. Okay, so there's a bunch of different examples that I want you guys to go through. Okay, it's from the summary notes of projectile motion. Stuff we've already been through. Maybe some stuff there's a bit extra that you can go through. Let's just have a look. Okay, yeah, you can go through the area as well. Okay. It's not absolutely necessary because we have our projectile motion formulas. But just take some time, go through it. Okay, if there's anything you guys would like me to go through, let me know and I can go through them. Okay, but it's just extra notes. You can have a look at different examples. Object dropped from height, object thrown from height, object thrown up from height, object thrown up and caught, object thrown up and lands at height, object thrown up from height and bounces, like I'm in. Okay, and it goes through all the different types of graphs for it. For now, let us do a question. So, this is actually a prelim paper because in Natal 2020. A ball is thrown vertically upwards from the top of a building with an initial velocity of 12 meters per second. The ball leaves the thrower's hand at a point that is 50 meters above the ground. The ball just misses the edge of the roof on its way down and it bounces off the ground. Just to clarify, okay, there's no need to be this specific, but it's fine. Remember, the thrower needs to, if it wants it to be perfect vertical projectile motion, he needs to throw it with his hand off the edge of the building. Then he needs to throw it up and it needs to fall straight down. Okay, whatever. But just to understand, we look at the diagram. Diagram just sort of does the archway thing. It's fine. So the ball just misses the edge of the roof on its way down and it bounces off the ground. Okay, so it's going to bounce. Now, ignore air resistance, which is the case in every single question that we do vertical projectile motion in. We ignore air resistance. Okay. So 3.1.1, determine the time taken for the ball to reach maximum height when it is thrown. So of course we're going to work, so maximum height is here. We are going to work with the motion from the initial throwing. We know what? We know that it was thrown with a speed of 5 meters per second to the -1. Okay, what else do we know? A ball is thrown vertically upwards, blah, 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 blah. It is 50 meters above the ground. Okay, so that doesn't help us, but this is a displacement maybe that we can utilize later. Now, the other thing we know is at the top, which is maximum height, we need to always remember. Okay, it's not necessarily V final, but V max or V at max height is equal to 0. The velocity at max height is always equal to 0. So here we actually know a V final and a V initial. Now in this question, you can do it in all your questions. I'm going to decide to take up as positive. There's no graph, nor do they specify and tell me take this as positive. So I am going to take up as positive. So up is positive. I know initial velocity. So let's write down what we have, right? Same approach. Doesn't mean this is an exam question. We should just absolutely fridge. V initial, I know. V final, I know. Acceleration, I always know. I don't think I know anything else. I know that I'm taking up as positive. That's important. Let us steal our, so again, what you want to do is you want to tear out your formula sheet from your question paper. Don't, so if you're writing like your final exam, you're going to get a booklet. Okay, so if you like tear it out on the edge, it's going to loosen the other page on the other end. So just take a ruler and on the edge of it, just tear it off completely. Okay, let's just steal our formulas. So you don't want to be like memorizing these formulas because why should you? Right? You just have your formula sheet next to you at all times and access the formulas. So should I take it with this or without this? I'll take it just with it. It's fine. Let's paste our formulas right here so they're in our face so we can access them all the time. Okay, what am I forgetting? I'm forgetting what we want. We want the time. We want delta t. So 4 things, right? You have to put what you have and what you need. The time taken for the ball to reach maximum height when it is thrown, 3-mark question. I'm looking for V initial. I'm looking for V final. I'm looking for acceleration. I'm looking for delta T. My first formula works perfectly. I'm going to utilize it. 3.1.1. V final is equal to V initial plus A times delta T. V final is 0 because it's at max height. V initial, I took up as positive, so it's positive 12. Plus my acceleration, because I've taken up as positive, I have negative acceleration. That's like something you want to memorize, then you can go ahead and memorize it. When you take up as positive, negative acceleration. When you take down as positive, positive acceleration. Okay, it's always 9,8, doesn't change in this section. Delta T is what I want to calculate, so I'll leave that as a variable. So when I take 12 over, I get negative 12 is equal to negative 9,8 because it's positive, and then negative 9,8 times delta T. I simply divide both sides by negative 9,8. And I am left with a delta T of negative 12 divided by negative 9.8. 1,22 seconds. 2 decimal places is perfectly okay. Is that correct? It is indeed correct. .1.2. Calculate determine the maximum height reached by the ball above the ground when it is thrown. So do not get fooled by this. Okay, please don't. It would be very nice. They say above the ground. 1.33. Are you getting 1.33? I don't think 1.33 is correct. Please double check your calculations. I believe 1.22 is indeed the correct answer. Can someone else confirm with me as well? Okay, perfect. Thank you. So the maximum height reached by the ball above the ground. So again, please don't get confused by this. So don't let this make you lose marks. Above the ground. So obviously we don't have any information right now, not much, right, between this part of the motion. We haven't worked with it yet. So if someone has to calculate the maximum height above the ground, we can calculate the distance it travels from initial motion, okay, where initial position to here. We can calculate this distance. Let's move this. Okay, we can calculate this displacement rather, and that would tell us the height above the platform. They want to know above the ground, so please don't forget to add your 50 meters to your final answer for it to be above the ground. Again, we are working with information that is from initial up until here. We can easily get that delta y because we have almost all the information for that motion, right? That's a very important indication in this topic as to which part of the motion you're using. Okay, it's where you have most information a lot of the time, most of the time. Sometimes it's weird, but where you have most information, you generally want to work from there. So that's what I'm saying. We can easily calculate the distance from the initial position of the ball to its maximum height. But the question specified, they said the maximum height reached by the ball above the ground when it is thrown, so above the ground. So when we calculate this delta y, this displacement from initial to there, we need to add it to 50 because then it would be above the ground, right? From there to there, and then from there to there. If they said above the platform, we could just give that answer that we get. Okay, enough talking. Let's actually do the calculation. So for maximum height, we know V initial, we know V final. Of course, we know acceleration. Now we use delta T. So if you can avoid using delta T, I would, just because you calculated delta T, and there's a chance it might be wrong. Okay, none of us are Einstein. So there's a chance it might be wrong. So just if you cannot use the previous thing that you calculated yourself, try not to. Okay, it's not the end of the world because a lot of questions, you actually rely on the thing that you calculated in the previous one. So that's what I'm saying. If you cannot use it, try not to use it so that you're more certain that your answer is correct. Okay, but we have delta T nevertheless. We want delta Y. So I think our options are endless. I'm going to use the third option, which has delta T, because I'm confident in my answer. We'll actually do both just to show you that you're going to get both the same answer. So let's do the second one first. So V final squared is equal to V initial squared plus 2A delta Y plus 2A delta Y. So V final, again, it's still max height. So it's 0 squared is equal to the V initial is positive 12. It's the speed at which it was thrown up with times negative 9,8 times delta Y. 12 squared is 144. I take it over. It becomes negative 144. This becomes 19,6, negative 19,6 times delta Y. I divide both sides by negative 19,6 and I have a delta Y, please correct me if it is wrong, a delta Y of 7,35 meters. That sounds wrong. No, it's right. Okay, so now remember, this is above the platform. Okay, so let's just do the other way so that you are confident that you can use both formulas. And even if you do use your rounded off time answer from the previous question, your answer is going to be extremely close to this answer, if not exact the same. The initial times delta T, even I don't know the formulas, plus half a delta T squared. Okay, so in this case, V initial is positive 12, delta T is 1,22 plus half into negative 9,8 into 1,22 squared. I'm going to put all of this directly in my calculator. And I get 7,35 rounded off. So I get the exact same answer. Okay, I'm forgetting the units, it's in meters. So my final answer, don't worry. Just showing you that you can get it utilizing the same formula, even with your rounded off previous time. It's perfectly fine. Now, what do we need to do? We need to calculate the height above ground. So the height above ground is going to be 50 plus 7,35. I think it's 50. We'll double check. It's equal to 57,35 meters. Please write neat and legible and make sure your final answer is no. So the final height above is 57,35 meters. Okay, let's move on to the next question. Calculate the velocity of the ball at t is equal to 4 seconds. Okay, so let's just consider this for a second, right? Since we have information, I'm trying to figure out, like, they're just saying t is equal to 4 seconds. Where is the ball at t is equal to 4 seconds? That's a question. Where is the ball at t is equal to 4 seconds? Let's try and see if we can imagine it. So firstly, let's get rid of this, right? The ball takes 1,22 seconds to get from initial position to max height. Okay, someone tell me, how long does it take for it to get to from max height back to where it initially started? How long does it take to get from max height to back where it initially started? I like color in this, you can tell me. One 1.22, 2.44. You guys answer quick. Yes, not 2.44. 2.44, maybe it is correct with what you are understanding. It's from initial to max height and then to initial again. That would be 2.44. But from max height to initial is another 1.22. Right? Remember, we discussed the symmetry in this. It's the same thing being thrown up from the ground. Right? This is the way I like to remember it, right? I used to always forget this. So how do I like to remember it? I think when I throw something up from the ground, it's going to reach max height and it's going to fall back to me. The time it takes to get from my hand to max height is the same time it's going to take to get from max height to my hand. Okay, it's the same distance, not displacement. It's the same distance. Okay, it's the same time. It's actually the same position also in this case because it's vertical projectile motion. So there, and then comes back down. Okay, so that's important to remember. So in total, right, that person said, so far it's 2,44 seconds. Okay, so it basically traveled, what is this distance? 7.35 meters plus another 7.35 meters. So it traveled about 15 meters, right? In 2,44 seconds. So they said they want to know where the velocity of the ball at t is equal to 4 seconds. So many of you, I feel like, would assume, because you're used to that question, you would assume that it's this velocity here. They're asking what's the final velocity before it hits the ground. Okay, which is not the case. This question is, it's not confusing, but it's just maybe too easy of a thing, right? So don't overthink it, right? They're asking literally 4 seconds. So 4 seconds after its motion, what is the question? It's velocity. That's what they want to know. Okay. So actually, after it reaches, it passes its point of starting, it reaches maybe like somewhere here, and that would be 4 seconds. Okay, like somewhere around there, right? We don't know exactly, but we just know it's somewhere still in its motion. Okay, so that's what we're going to utilize. So firstly, the first thing that we do know is delta t. We're literally just going to use delta t as 4 seconds. Okay, 3 marks, velocity. So we want to technically calculate final velocity, okay, because we're not starting like here, for example. Oh, sorry, we're not like ending here and starting there. We're going to end here most likely because our initial is going to be somewhere here. Okay, now we know V initial, we know acceleration. So that should be enough to use it. We know delta t, V final, V initial, and A. So the first formula is one that we're going to choose, right? Because it has all 4 of these things. Now, our V initial, okay, let's write out our formula, right? So this is 3.1.3. V final is equal to V initial plus A times delta t. Okay, so V final is what we actually want to calculate at 4 seconds. Now, V initial is tricky. Okay, we can actually start wherever we like. Okay, so I'm going to start here. I want you guys to tell me, right? I'm going to do all 3. Just no, I don't do all 3. It's too much. Let's just discuss it and we'll choose one. So I'm going to start at the initial position of the ball. Okay, 2 things. Someone tell me. Okay, I also have delta y, but it's fine. Someone tell me, I'm going to start there, right? What is my initial velocity if I start here? If I'm starting at when the ball was first thrown, what is my initial velocity that I need to substitute there? Actually, no. This is okay. Okay, correct. 12. Very good. 12 seconds. Okay, I mean 12 meters per second to the -1. Very good. Positive 12 is the main thing, right? Nobody said negative 12. Okay, somebody said 0. No, 0 is at max height. Okay, so here I can substitute now 12, positive 12. Plus acceleration, always negative 9,8. Nothing wrong. Cool, moving on. Delta t. Now let's read the question. Velocity of the ball at t is equal to 4 seconds. There is something that's very important that you guys need to understand in this section. We deal with something called a time frame. Okay, so when they say t is equal to 4 seconds, it's like on a number line. Okay, it's like on a number line. So here's the first second, 1 second. Here's the second second. Here's the third second. Here's the 4th second. So the initial onset of the ball was here at t is equal to 0. Okay, now they want to know how far did it travel in 4 seconds. So in 4 seconds. Now, do you see at t is equal to 4, that's this here. It's when they say t is equal to 4, this is a t number line. Okay, it's a t number line, and t is equal to 4 is actually from the beginning of the motion. They're not saying it like they're not specifying, they're saying 4 seconds after max height. They're just saying at t is equal to 4, so that you need to assume that it's from the onset of the motion. Okay, so from the beginning. Okay, so in this case, it starts here. They want to know after 4 seconds of travel. So like something like this. from the initial. From the initial. So if we are going to utilize 4 seconds as our time, then we have to use positive 12 as our initial velocity. Why? Because that was the start of the 4 seconds. This is t is equal to 0. T0 here. 0 seconds. This is when it was 12 meters per second. This is the velocity. Then it went all the way to 4 seconds. And then that's the velocity we need to calculate. Okay, so let's continue. Basically, we just have to do this calculation. So 12 plus negative 9.8 times 4. This is going to give us a final velocity. Okay, someone tell me, okay, you guys might have done the calculation, but it's fine. What kind of velocity are we expecting? Are we expecting a negative velocity or are we expecting a positive velocity? Okay, why are we expecting a negative velocity? Why are we expecting a negative velocity? Exactly. So up is positive. We chose up is positive and it's going down. So it's traveling in the downward direction. So we're expecting a negative velocity. So please, if you need to have that understanding when you're approaching the question, right? Be like, okay, I need to expect a negative velocity. So when you do your calculations and if you're getting a positive, you need to know that something is wrong, even if you are using, even if the magnitude is correct. So negative 27,20. I'm just putting the 0 because it looks nicer than just a 2. Final velocity is negative 27,20 meters per second. We would say that our final velocity is 27,20 meters per second to the negative 1 downwards. Okay, I'm going to do this a different way. You don't have to do it this way, right? Like I would like, this is the easiest, fastest way. Done, khalas, right? But we can do a second way just for you to understand it, right? Now let's do it because acceleration is negative. Very good. Okay. So now what if our initial is different? What if our initial is here at the point where it returns, because we have a lot of information, right? So maybe we want to work with our initial here when it returns to where it is. Okay. So tell me, we're going to use the same formula. Okay. V final is equal to, time is flying, V initial plus A times delta T. Okay, so V final is what we want to calculate. Now tell me, when I start here, at the point it returns to, what is my initial velocity? I'm asking for velocity, not speed. What is my initial velocity? What is my initial velocity? I'm not seeing enough answers. I want more answers. Are people not confident? Okay, correct, right? Negative 12, right? It's negative 12 because of, again, of symmetry. Remember, it was released at this position with a speed of positive 12. We said that, that's one thing I forgot. When I was doing this diagram, the velocity that it's released with, let's just, the magnitude of velocity that it's released with is the same as the magnitude of velocity that it comes back with at the exact same position. So like I've annotated here, if it's a positive velocity, it will come back traveling with a negative velocity, but the same magnitude. Okay, the same magnitude. That's the symmetry in that motion. Thrown up from the ground, for example, you throw it up, the time it takes to get to max height is the same time it takes to get from max height back to your hand. The speed at which you throw it with is the same speed at which it lands in your hand. The velocity at which you throw it with has the same magnitude of the velocity that it lands in your hand. It's just that the directions are opposite. Initially, it's traveling up and now it's traveling down. So here, when it reaches this point, the velocity is negative 12 meters per second to the negative 1. Okay, that exact same position, it's negative 12. So now, in this case, I'm going to have to substitute negative 12. Okay, acceleration doesn't change. My acceleration is still negative 9,8. Now, what about time? What am I going to substitute as time? Because this is my initial. I'm starting off here. What would I have to substitute at time? Okay, also, like, you might feel like it's redundant to go through this because we've already solved the question, but there are some questions where, just say you didn't know the initial velocity and you are forced to start here, then you need to understand these concepts. Okay, so when we are starting here, tell me, what time am I going to use? Because remember, I want the time of my entire motion. So I need the time it takes to get from where I start to where I end. That's the time I need. Is it going to be 4 seconds? Does it take 4 seconds to get from the negative here? Let's label them, right? Let's call this A. Let's call it B. Let's call it C. And then let's call this D. Okay, excellent, right? So this is where the concept of timeline comes in, okay? You need to understand that this is always working with the timeline. So what do I mean by that? Let's go to this little timeline we drew. Remember, the ball travels for 1,22 seconds, which is somewhere here. And then what? It reaches max height. Okay, initially it's at A, max height is at B. Then it travels another 1,22 seconds, which goes to 2,44 seconds. Okay, it reaches C. I'm just going to call it C. Let's not write long stories. It reaches C. Now it's going to what we want to calculate. It's going to 4 seconds, which is where we want to. D is this made up position we made. Okay, we called it D. Okay, so this is very important. If our initial was actually at C, the time it took between C and D, that's what we need to calculate. And that's simple to calculate. Okay, okay, we can say 4 seconds minus 2,44 seconds, and that's equal to, I trust you guys maths, you say 1,56. 1,56 seconds. So to get from C to D, it's 1,56 seconds. Again, this is not 100% necessary. The person that said 4 minus 1,22, do you understand now why it's actually 4 minus 2,44? Okay, it's not extremely necessary to do it this way, but it's important to understand how vertical projectile motion and questions like this work on a timeline. Okay, so therefore, I have to use, and you'll see we'll get the same answer. I have to use 1,56. If you want to do it yourself, you may do it in the calculator as well. I'm going to do it quickly. Negative 12 plus negative 9,8 into 1.56. And I get an answer of negative 27,29 meters per second to the negative 1 to the negative 1. Yeah, that's correct. And then it's slightly different, but there's different methods, so you can expect different answers. Nothing wrong. So it means you're going to get it wrong. As long as your calculations are all correct, there's a margin of error where they'll give you the correct answer. Downstairs, my head downwards. Okay, let's try and finish this last question. 3.14, the position of the ball above the ground at t is equal to 4 seconds. The position of the ball above the ground at t is equal to 4 seconds. Okay, so we have now the final velocity. Okay, so let's consider what we have at t is equal to 4 seconds. If we're going to work from the initial, we have delta t. We have v final. We have a v initial for sure. We have acceleration. We have no passion. Delta y is what we want. That's what I forgot. Delta y is what we want because they want the position of the ball above the ground at t is equal to 4. Okay, so I'm going to utilize this formula. It doesn't even need v final, this formula, by the way. Is that fine? Yeah, that's fine. So I'm going to say 3,14 delta y is equal to V initial times delta t plus half a delta t squared. Okay, so this is going to calculate for me the displacement from the initial. So when I start at A, it's going to calculate the displacement up until B. Please, it's not calculating distance. It's not going to tell you how far it traveled to B, how far it traveled to A, how far it traveled to D. No, it's going to tell you the distance between where you start and where you end. Okay, that's what this formula is going to give you. My V initial is 12. Okay, my delta T is 4. Again, I can use 4. I can use the other method, but I don't want that headache. Acceleration is negative 9,8 because it's in the downward direction. Delta T has to be positive and it's 4. So I'm going to do this calculation. It's going to be, okay, firstly, before I calculate it, am I expecting a positive or a negative answer? Quickly. Am I expecting a positive or a negative answer? Negative, positive, negative, 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 positive, positive. Okay, the correct answer is positive. No, it's negative. So basically, how we consider this really quickly is, where are we starting? Okay, we are starting at A. We are starting at A. Where are we ending? At D. So if I consider my starting point, my end point relative to my starting point, it's down. From where I start to where I end is in the downward direction. So I will have a negative delta y because I've chose downwards as negative, of course. Well, up is positive and then downwards is negative. So I have a negative delta y. So that's exactly what I get. I get negative 30,4 meters. So it's basically telling me the displacement from A to D is negative 30,4, which is perfectly fine, right? They wanted to know the position of the ball above the ground at T is equal to 4. So now remember, from A to D is (30,4 meters. So therefore, so it's a lot more down, but it doesn't matter. From there to there is going to be basically 50 minus 30,4, which is equal to 19,6, I think. Is that correct? Anyone? Okay, so yes, 19,6 above the ground. Why? Because the question specifies how far above the ground it is it. So I know this kind of doesn't look like 19 and 30, but it doesn't matter. It was all just estimations of where D was. So clearly D is somewhere lower, closer to the ground. Okay, but nevertheless, we have, I'm not going to write all the long stories because we are late. 19,6 meters. Okay, perfect. Okay, so next time when we come, we're going to do this velocity versus time graph. Maybe we can spend one whole other lesson on velocity, vertical projectile motion. I know we haven't gotten to organic, but yeah. Can you please explain how the displacement is negative when up is positive? Okay, I'll explain it now. Okay, so we'll do that, and then maybe a position versus time graph. Let's see how it goes. Okay, so someone wants to explain why the displacement is negative. So I'm just going to redraw something here on the side. I'm going to call this, it's an egg. I'm going to call this B. I'm going to call this C. That's another egg. I'm going to call this A. Okay, so let's just say I'm traveling from B to C. Right, I'm going to try to make this a basic explanation. If I'm overall, I've chosen up as positive, okay? So if I travel from B to C, okay, I'm traveling downwards. Down is negative, which means negative displacement. If I'm traveling from B to A, I'm traveling upwards. Up is positive, so therefore positive displacement. Okay, I'm just going to leave it at that. Yes, okay. That's why we rather just allocate a whole another lesson where we can do a 2-ball situation. Okay, cool. So, yeah. Okay, we leave it at that. I will see you guys next week. Okay, where we'll do the same topic, and then we'll move over to organic. Before we leave, I have a really important question for today. What do you guys have for Manchester United versus Liverpool? Who do you guys think is winning? Any soccer fans? I'm assuming they're soccer fans. Spaceman can't be negative unless it's opposite, but Liverpool, Man United, Liverpool, yeah, okay. Man U, Liverpool, Man U. Okay, not bad. Okay, it's split 50-50. Okay, let's see, right? If it was wrong, I'm giving them 50 questions of homework. Okay, cool. So anyway, let's end it there. I'll see you guys next week. Thank you guys so much for joining. Have a good week of school. And yeah, for someone asked about extra physics classes. I think we're going to let you guys know by today, and then we'll take it from there. I would recommend you guys try your best to join them. Okay, so that just, it makes it easier so that we can do harder questions in those. I mean, no problem. Jazakallah khair, guys. Assalamu alaikum. Thank you and goodbye.